The typical atom, as we know it, consists of a nucleus and one or more nucleobound electrons. This idea has been around since the early 1900s, and while it's not incorrect, it lacks depth. The true structure of an atom is far more complex than physicists originally thought, and in the mid to late 1900s, physicists discovered several particles from which atoms are made. First, the nucleus must be viewed as a grouping of particles, protons and neutrons. Then those particles would further consist of elementary particles called quarks.
The proton, for example, consists of 2 up quarks and 1 down quark. Quarks serve as the building blocks for matter as they are fundamental and have no substructure. In composite particles like baryons, the proton and neutron for example, the quarks within are bound by the strong nuclear force. The theory concerning this interaction is known as quantum chromodynamics, or QCD. To understand the nature of this interaction, color charge must first be understood. Physicist Wolfgang Pauli formulated the Pauli exclusion principle, which effectively states that identical quarks cannot exist in the same system. Since the proton, for example, contains 2 identical quarks, there must be another property setting them apart. To obey this principle, it was proposed that quarks shall carry one of 3 colors: red, green, or blue. In a composite particle, like a baryon, the quarks must have different colors, making the net color neutral. Before color charge, the identical up quarks in a proton would violate the Pauli exclusion principle. After color charge, however, the 2 quarks are now different, so they can exist in the same system. Problem solved, but color charge doesn't end there. Color charge also describes the existence of anticolors: anti-red, anti-green, and anti-blue. Particles called gluons carry both a color and an anticolor. Gluons are force-mediating particles that quarks exchange to bind to one another. And the exchange of gluons must conserve color charge, however, so when a quark emits or absorbs a gluon, it must change its color. Here's an example. Let's say the red quark on top emits a red anti-green gluon. In order to conserve color charge, it changes into a green quark. The gluon connects with the green quark, and the anti-green of the gluon balances with the green of the quark, so the quark turns red. Looking at the system after this exchange, we can see that the net color is still neutral, as all colors, red, green, and blue, are still present. Gluon emission and absorption occurs constantly, with all quarks exchanging gluons with each other, while preserving overall color neutrality. The exchange of gluons binds the quarks together with a force much stronger than that of the other forces.